Okay, so as the exam is approaching, I will, on Wednesday, let me put some official office hours. Wednesday from 8:40 up to, let's say, 11:40. I will be in my office, and if you have any questions, well, I will try to arrange another office hour some other days. But if you have any questions, and those who don't have any lab, well, Saturday you have the exam. If you are willing to come before, so on Wednesday, do all of you have the lab? Yes. Okay. Fine. Okay, let's see. On Thursday, I have a midterm on my other course. So on Wednesday, at that time, I will be in my office. So if you are willing to ask questions, you are welcome. Don't skip your labs, though. Well, another thing that you shouldn't skip is that, I mean, we have been talking about how we can improve the success of the students in various courses like the general physics, the calculus, chemistry, and these are basically the courses the majority of the university students are taking. And in all of these courses, the corresponding departments are kind of not happy with the overall success of the students. Now, we are discussing what we should do as the instructors, how we can improve ourselves, and at the same time, what the students should or shouldn't do. And it seems that apparently there is a general behavior pattern in a significant number of students, let's say. So what happens quite often is that when the midterms start, did you have a calculus exam last weekend? No. Okay, this will be your first exam, right? No, chemistry. Okay, you had the chemistry. Now this weekend you will have the physics. Most probably the following weekend you will have the calculus, and the following weekend you will have the English, and then back to chemistry, physics. Practically from now on until the end of the semester, your weekends are occupied. So what a significant number of students do is when it's the time for the chemistry exam, you start skipping all the other courses, and then you study for the chemistry exam. Then the exam passes, then it's the time for the physics exam. So you skip all the other courses except then the physics. So today, the number of students, there has been a slight increase compared to last week. But then, since you have already missed 1 week of the physics course, all the material that you need to study will be new to you, so you have to learn them on your own. But that is not effective in learning, so you have trouble learning the material that's covered during the classes that you have skipped. And then it is the next week, it will be the mathematics course, but you have already skipped 2 weeks of calculus. So, and then it's basically a chain reaction, and at the end of the day, you basically fail in all of them. So I would advise you strongly against that. I mean, even if you cannot study regularly, let's say this weekend you have the physics exam, you will probably not have time to study for the calculus courses during this week, but still you should go to the calculus course so that at least you will have an idea of what is being covered. So when you are studying it, you will already know something. It will not be completely new. The same thing for the physics course. This weekend the exam will be over, so I strongly advise you to keep attending the physics course next week and the other weeks. Okay, back to our subject. Any questions? If you remember, last Thursday we were discussing last week we started discussing the potential. And just like the electric field is, in a sense, closely related to the force, the potential was closely related to the potential energy. And just a warning, the names are also quite similar. I mean, the potential and potential energy are different things, although they have one word in common. The potential, in a sense, is the potential energy per unit charge, just like the electric field is the force per unit charge. So if you know let's say, if you know the potential at everywhere in space, there's a charge distribution. These create some potential around them. And if you have a test charge that starts from the point, let's say, RA, and you just move it to the point RB. So here you have the potential. That point has the potential VRA. This point has the potential VRB. The work done, the work that you have to do to carry that charge Q from the point RA to the point RB would be just Q times VRB minus VRA. So this is the potential difference. And in terms of the electric field, we had seen that the potential difference between those 2 points as you go from A to B is defined as minus the integral of the electric field from the point A to the point B. One special case of this was if the electric field is constant. Well, you can just take the constant out of the integral, and VAB is just minus E, the integral of dl from RA to RB. So this is minus E times, let me just write, your displacement as you go from point A to B. Or sorry. Now, any questions about these? About the concept of the potential? Now, in particular, on Thursday, we had also discussed and extended a spherical charge. Let's say if it's a conductor. We said that V, the potential, okay, first of all, since we can only calculate the potential differences, you see here, this only tells you the potential difference between 2 points. It doesn't tell you the potential at a given point. You always need to choose a reference point as your, to define your potential. So in general, the reference point we choose will be at infinity. So the potential is equal to 0 at infinity. If we choose the potential at infinity to be 0, we had seen that the potential at a given point was a Q over 4 pi epsilon 0 times 1 over R if you are outside, and Q over 4 pi epsilon 0 times 1 over the radius if you are inside the sphere. Well, it's a conductor. So we said that inside the electric field is 0. But even if the fact that the electric field is 0 just tells us that the potential inside is constant. There's no potential difference inside. So whatever the potential is on the surface, it's the same potential throughout the conductor. That is why we have the potential inside. Although the electric field is 0, the potential is not 0. Of course, saying that the potential at a given point is not 0 doesn't really mean much, because since we are free to choose the reference point of the potential, we could have defined the potential inside the conductor to be 0, but in such a case, the potential at infinity wouldn't be 0. So this just tells me that the potential at infinity and the potential inside the conductor are different, at least in this example. And now we said that, okay, so this is the electric field. We compared that with the magnitude of the electric field. So on the surface, this is our electric field. So you see, on the surface, the electric field and the potential, they are simply related by a factor of the radius. You see, up to this point, we have been talking about the charges. We had discussed how we can charge an object. If you have an insulator, you can just rub it on some other surface, and then one surface will acquire electrons, so it will be negatively charged. The other surface will be left with a positive charge. But in general, it's not so easy to just determine the charges. How much charge do we accumulate on a given region or on a given object? What we usually do is we determine the potential or the potential difference between 2 points. Now, when you think about the electricity, most of the time you just think of either those plugs over there or you just think of the batteries. Now, what battery does is that we will be studying the batteries and circuits later on, but the battery creates a potential difference between the 2 points. It doesn't create a given charge, it doesn't create anything else, but it creates a potential difference. So basically, when you connect a conductor to a battery or a circuit to a battery, you are fixing the potential difference. And then the charges move around whichever ways, I mean, depending on how you created what is that system. But at the end of the day, they will settle or they will behave such that those 2 points, the potential difference is fixed by the battery or the plug. The plug just fixes, in Turkey at least, the potential difference. It creates a potential difference of 220 volts on the average. For a battery, if you just take these cylindrical small batteries, they create a potential difference of around 1.5 volts, depending on the type of the battery, 1.4 or 1.5 volts. You fix the volt. Now, what does this tell me? In the case of these conductors, let's say, for a given voltage, if the radius is smaller, it means it's creating a larger electric field on the surface. You see, if this is fixed, if R is small, then you have a larger electric field. If R is large, you have a smaller electric field. Well, why is that important? Well, just take a sphere. Suppose you have your sphere over here. And you can just imagine 2 spheres if you like. Put 2 spheres, you connect them through a battery, so you are fixing the potential difference between those 2 spheres. If these spheres are very small, then on the surface of these spheres, you will be creating a huge electric field. But you see, there is air everywhere. If there is air everywhere, air is made up of atoms which contain positive and negative charges. If you put these positive and negative charges in an electric field, they will try to move in opposite directions. But of course, the charge of the nucleus will just keep all the electrons bound to it. But if you apply a large enough electric field, the electric field can just separate one of the electrons if it is large enough. Because the atom, if you consider the oxygen atom, for example, it has, what is the electron number? It has 8 electrons. So if you apply a large enough electric field, then you can just separate one of the electrons from the oxygen atom. So you have one positive charged object and one negatively charged object in a huge electric field. So they will accelerate, collide with other atoms, and then it will also separate the electrons in the other atoms. So you have all this current flowing in air. So that is basically what the lightning is. And what the lightning rods do is they have, at their tip, the radius is very small, so they create a huge electric field, even for a very small potential difference. So without accumulating too much charge, you create this current and discharge the clouds. So that basically tells me that if you have, let's say, a pointed object, you cannot put too much charge on it. Because if you put too much charge on it, you will be creating some potential difference, a decent potential difference, which will create a huge electric field. But that huge electric field will ionize the air nearby. If it ionizes the air nearby, then there will be a current, and all the charges that you accumulated will just run away. So in a sense, if the radius is very small, your capacity to store charges on it will be limited. You cannot put too much charge. If you put too much charge, it will just go away. If the radius is large, in that case, you can store lots of charges on that. This is what we call the capacitance. Basically, it measures the ability of an object to store charge. So we would like to define the capacitance in this way. So it's just a measure of how much charge you can store it without discharging. So for example, back to this example, you would expect the capacitance of a large sphere to be more than a small sphere. Because if you have a large sphere, R will be large. For a given potential, the electric field will be smaller, so you don't get the ionization of the air nearby. So the charges in that sphere will stay there. Now, mathematically speaking, we define the capacitance of a system as Q over V. Well, the electric field, our discussions over here was mainly based on the electric field. So what you want is an object with a large capacitance to create a small electric field for a given potential difference. But the electric field being a vector, we cannot really use it to define a number. So, okay, we define the magnitude of the electric field, etc. But nevertheless, this turns out to be a better description of capacitance. So what happens for a given charge distribution, you have to determine what is the voltage. The ratio gives you the C. Now, let's apply this. Okay, this definition already might be a bit vague. Let's apply it. So because the meaning of this charge Q will also be somewhat vague. For example, the capacitors which are objects that have the capacity to store charge. Well, the capacitors will be neutral in general. What they will do is you will have one charge in one side and the other charge on the other side. We had already seen one example of this. We had already discussed the parallel plates. If we put some charge over here, let's say plus sigma charge density, and we put a minus sigma on the other side, well, the system is neutral as a whole. But this plate has some charge, and this plate has the opposite charge. So still, in a sense, we are storing charge in different plates. What was the electric field created inside? Sigma over epsilon 0. What is the potential difference if they are separated by a distance d?
E times d.
It's just E times d. You see, the electric field is uniform, is constant. If the electric field is constant, the potential difference is just minus E times d. Well, in the capacitance, we don't really care about the sign of the potential difference. We don't really care which plate has a higher potential than the other one. But the difference in the potential of the plates will be just the electric field multiplied by the distance. Well, actually, it will be, let me put an absolute sign, minus E dot D. It's the scalar product. So it's the distance in the direction of the electric field. So this is just E times D. Well, ideally, in this, we assume that we have an infinite plate. Well, in practice, no plate is infinite. So it will be a finite plate. But this infinite plate approximation will be a good enough approximation if this distance is much, much smaller than this distance. So we will be assuming a very large, very nearby plates. So this approximation will be still good enough. If it is a finite plate with an area, let's say A, what is the charge? Well, the charge of this plate is plus Q. The other one has a charge minus Q, where Q is just sigma times the area. Now, the capacitance we had defined as Q over V, which is, well, Q is sigma times A, V is E times D, where the electric field is sigma over epsilon 0 times D. So the capacitance is epsilon 0 A over D. Well, does it make sense? Does it relate with our before arguments that the capacitance should be a measure of how much charge you can store in a given system without causing electrical breakdown of the material in between? Well, let's see. For a given potential difference, so you just connect it to a battery so that you know the potential difference between the plates. We want the electric field to be small. For a given potential difference, if the electric field is smaller, then that system has a larger capacitance. So let's see. If we fix the potential, if D decreases, E increases. Or if D increases, then E decreases. So the larger the D, the smaller the electric field. And hence you can put more and more charge until you reach the critical electric field. So the capacitance, if you have a large D, then the electric field will be small. And you have a, did I make a mistake somewhere? Let's start with A. If you have a large area, sigma will be small, so the electric field will be small. So you can add more and more charge. So it makes sense that capacitance is proportional to the area. If D is small, the capacitance again increases. Well, let's see, if D is small, the electric field increases for a given potential difference. What's our mistake? Anyway, so what's the problem with D? Let me just skip this. I don't have the answer now. So let's not wait and lose time. Okay, so at least the proportionality to A, in a sense, makes sense. Larger the A, the more you can store. The inverse proportionality to D, well, it is more related with, since they will be closer to each other, they will attract the charges together. So it will be easier to charge them, but let's just skip it for the time being. Now, any questions on how we calculate the potential difference? The capacitance, sorry. You just put some charge to your system. So that is what we did. We put some charge to our system. Plus sigma, minus sigma. And we calculated the electric field and obtained the potential difference. So once we obtain the potential difference and the total charge, the capacitance is just their ratio. So whatever system you have, this will be the strategy. You put some charge to the system, determine the corresponding potential difference, and take the ratio. That gives you the capacitance of the system. Now let's apply this to a different system. A spherical capacitor. So it's essentially, we assume that we have two spherical shells, conducting spherical shells, one inside the other one. We put a total charge, let's say, plus Q on the inside and minus Q on the outside. By definition, capacitance is a positive quantity, so it doesn't really matter which shell is positively charged, which shell will be negatively charged. So on the surface of this sphere, you get the positive charges. Well, the charges move to the surface because it's a conductor. On the outer shell, the total charge will be on the inner surface. This is our capacitor. So we first have to calculate the potential difference between the inner sphere and the outer sphere. Well, let's see. Here we have positive charges. They will attract the negative charges. So that is why they are on the inner surface. This, or you can say that, okay, this is all, let's just imagine this region is a conductor. There shouldn't be any electric field there. The electric field in this region should be 0. But if the electric field in this region is 0, that tells me that if I imagine a Gaussian surface going around, the Gauss integral will be 0. So the charge will be on the has to be on the inner surface. It cannot be inside the conductor. Still, there has to be a minus Q charge on this inner sphere because the Gauss integral is 0. If you just, let's say, if you just imagine the outside to be a conductor of some finite thickness, imagine this Gauss surface. Since it's a conductor, the electric field at that point is 0. Inside the conductor is 0. So E dot ds, the integral of the electric field over that Gaussian surface, should be 0 because the electric field is 0. But that tells me that the total enclosed charge by that surface should be 0. So plus Q charge is over here. I have to have a minus Q charge within this red sphere. And the only place it can be is on the inner surface. Now, what is the electric field, let's say, at this point? At this point. Why should it be 0? You see, here we have a conductor. Here we have a conductor. But this is empty space. So you see, outside the spherical charge distribution, we had said that if you are outside, the spherical charge distribution always behaves like a point charge. So if we are looking for the electric field at this point, we can just imagine this sphere to be a point at its center. So the electric field here will be the electric field created by that point charge. And furthermore, we also said that inside the sphere, if we are inside the shell, you see, we have charges also in this shell. We are inside that shell. That shell doesn't create any electric field on this inside it. So at this point, the total electric field will be the electric field created by this one, plus the electric field created by these charges. But these charges do not create any electric field inside. So it's only the electric field created by this charge at this point. So at this point, the electric field is that of a point charge at the center. You see, if you look at the point outside, out over here, again, the total electric field created by this system will be the electric field created by this spherical object, which will act like a point charge. Since it's positively charged, the electric field at this point will be pointing away. And now we have this spherical charge distribution. Again, since we are outside that spherical charge distribution, it will behave like a point charge at its center. The total charge is minus, so the electric field created by this outer shell will be pointing towards the shell. So we have one electric field pointing outward, the other electric field pointing inward. They are both equal to the electric charges created by plus Q and minus Q charge at the same distance, so they just cancel each other. That is why outside we will have zero electric field. But inside, only this charge distribution creates an electric field, so we have a finite electric field. At this point, neither this charge nor this shell, none of them create electric field at this point. So inside the conductor, we end up having zero electric field. Now what we did, we had a charge Q. We put it in our system. Well, we, in a sense, separated the charges, charge plus Q over here, minus Q on the outside. Now we have the electric field created by that charge distribution. The next thing is we have to calculate the potential difference created by the charge. Since the electric field is proportional to Q, the potential difference will also be proportional to Q. And when we take the ratio, what remains will depend only on the geometry of the problem and not on how much charge we put. Well, let's calculate the potential difference, let's say between the points A and B. This is VB minus VA, which is minus from the point A to B, the integral of E dot dl. Well, let me move the point somewhere else. Well, we had already discussed that this integral is independent of how you go from point A to point B. It's up to you. Whatever path you take, it will give you exactly the same answer. So to simplify the computation, I will choose a path from A to B that first moves in the direction of the electric field, that is radially outward. And then when I am at a distance of the point B, I will, or if you like, you can just imagine going inside, then I will just go along a circular arc, so that I will always be, the displacement will always be perpendicular to the electric field. This is the path I will imagine. First, I go radially up to the distance of the point B, and then I go along an arc. Well, the advantage of this path will be, let's say now I divide the path, the integral from A to P, and then from P to A. P to B, sorry. You see, from P to B, as I'm going along the arc, the electric field is always perpendicular to my dl. So these two vectors, they are perpendicular to each other. So this integral just gives me 0. There is no contribution to my integral as I go from P to B. Well, it makes sense because P and B, they are at the surface of a conductor. And since they are at the surface of a conductor, and we had already said that the surfaces of any conductor, whatever the shape is, the surface is always an equipotential surface. So there is no potential difference between the point P and point B. It is this integral, should be 0. Now let's continue from A to P. As we go from A to P, E and the L, they are both pointing in the same direction. So the scalar product is just from minus A to P, the magnitude of E multiplied by the magnitude of the L. The electric field magnitude is 1 over 4 pi epsilon 0 Q over R squared. dl, if I imagine such a segment, dl is the length of that segment, but that is also the change in the radial distance as I go from one segment to the other segment. So dl is just change in the radial distance. And the radius, let's say the inner radius, let's just assume that my sphere has a radius A and the shell has a radius B. So this integral goes from A to B. So the potential difference between the shell and the sphere is 1 over 4 pi epsilon 0 Q over R, as R goes from A to B. Q times 1 over B minus 1 over A. Now, what we had done, we had our system. We put some charge on our system. And then we calculate the electric field created by that charge. And using that electric field, we calculated the potential created by that charge. Now, the capacitance is just Q over V. Q is just Q. The potential difference created by that charge is 1 over 4 pi epsilon 0 Q times 1 over A minus 1 over B. Well, I just reverse this 1 over B minus 1 over A, because here the V is just the magnitude of the potential difference. We define the capacitance to be positive. That's why I just reversed them. This is the absolute value of that potential difference. And charges, they cancel. The capacitance turns out to be 4 pi epsilon 0 AB over B minus A. So this is the capacitance of a spherical capacitor. Now, sometimes we also define the capacitance of a single sphere. So we just have this capacitance. We put a plus Q charge over there. Now, in this case, we still imagine two spheres, one sphere and the spherical shell outside, but we just imagine the outer shell to be at infinity. So in this case, the charge is over here. The potential difference will be the potential between this point and at infinity. So in fact, this is nothing but limit. So we already had calculated a shell and the sphere. B is the outer shell. So we take the limit as B goes to infinity. So the capacitance of a sphere is in fact proportional to its radius, as we had argued before. Questions? Any other questions? Now, before you go, let's look at another example. Cylindrical capacitor. Well, in this case, instead of a sphere, you have one cylinder of length, let's say L, and then you have another cylinder around it of the same length. Let's say the inner cylinder has a radius A, the outer cylinder has a radius B. Basically, the calculation strategy is identical. You put some charge, let's say plus Q inside and minus Q outside. Then the charge, the electric field created in the region in between, we had already studied it. It was lambda over 1 over 2 pi epsilon 0, lambda over r. This was the electric field created by a cylinder. In this case, lambda is just Q over L. So we put a charge Q, which will be uniformly distributed over the surface of the cylinder. So the linear charge density is just Q over L. The potential difference, again, I will be just ignoring some signs. It's just the electric field, lambda over r, as we go from the inner shell to the outer shell. And the inner shell has a radius A, the outer shell has a radius B. So this is 1 over 2 pi epsilon 0. Lambda is Q over L. And the integral of 1 over r is just the logarithm of r, as r goes from A to B. So this is equal to 1 over 2 pi epsilon 0, Q over L, logarithm of B over A. Well, the capacitance is just Q over V. For a given charge, the created potential difference is 1 over 2 pi epsilon 0, Q over L, logarithm of B over A. Q's cancel, and what you have is just the capacitance. This is not a sphere. This is an infinite wire. You see, this is the electric field of an infinite wire. Of course, the exact expression for a finite wire will be slightly different than this. But as long as this length is very small. As long as you are not very close to the edges, you will not really feel any deviation from this expression. If it was a sphere, we have the 4 pi epsilon 0 r squared. Yes, any last minute questions? Did you get an email about what will be covered in the exam? You will probably get it today. Okay, see you on Wednesday, Thursday, and Friday.